what I've got planned to do this session is cap off what we were doing last session before the half-term holiday. So I left with you looking at a problem around a three-phase delta connected system where you got a loss of line fault. So we've done loss of line fault for three-phase star and neutral, but not the delta. And then the rest of this session pass over to, I got a sheet here with 3 typical exam questions on to have a go at and get an early look at what typically the exam questions are going to look like and what the range of marks is. So I plan to just talk you through very briefly about the overall content of the exam, how long it is and so on, and then let you have a first go. And as the session go on, we can look at specific parts of those questions you might get stuck on up on the board or whatever. So a bit of an interactive look at those and a discussion about how long you'd end up having to answer each of those questions. I always think it's important to get in the habit of having to do that style of question under some kind of time pressure. Yeah? Okay. So that's what I got planned for this session. So, at the end of last time, we left you with that, which I changed the order a little bit because I had the practical rig up set up for star, so we jumped to the star system. And actually the star problem is slightly easier to deal with anyway than this one. So load connected in delta as per problem 1. So a balanced load, develop the fault where one line has gone open circuit. Sketch a diagram of this fault system and determine those 5 things. Current flowing in each of the remaining lines, new current in each load, new power dissipated by each load. Comparing that with problem 1, new total power dissipated by the system under fault conditions, and compare the total power of that from problem 2. So has anyone had a full go at that? That's right, Danny. Did you get a chance to have a go at the problem we left last time?
I haven't.
Okay. What we'll do then, right, is we'll do it together. You're going to do the biggest majority of the work, hopefully. Alright? So, I'm going to pause this for a minute and we'll get the diagram up on the board and then we'll start from there. So, that is the system we got. So, effectively, we've got a pair of phases, the red and yellow, supplying 300 volts to that delta network. And the blue phase is gone. So what are we looking at there? How can we deal with this problem now? Is there another way that we could draw that more conventionally that would help to solve this problem? Because now we've only got a single phase system almost connected to a delta load. We've only got one lot of 300 volts here to deal with. No voltages out of phase with each other. What we've got is we've got a 950 here, this resistor, in parallel with these two in series. Yeah. So what we're suggesting here is you can simplify this diagram to this. 300 volts. That, and if we all label them all R and say R equals 1950, we've got our system in a more conventional way of drawing it. because that don't really matter now, showing that that's a delta in a way, and we've not got three lots of voltages 120 degrees out of phase with each other. That complication has gone. So that's our circuit, and that's what we're looking for. So what could we say? It says find the current flowing in the remaining lines. These are the lines, one there, one there. What could we say about the currents flowing there and there? They're the same, they're equal to each other. The current in the because this was the red phase, this was the yellow phase. So if it's delivering current along here, it's travelling through that resistor network, some this way, some that way, but eventually all meeting up down there. Again, it's just a simple AC network now with one voltage source. So if we call this I yellow and I red, we can simply make the statement I yellow is equal to I red, yeah, because that's simple network. But how are we going to find that current? Yeah, so it's going to be E over RT. Yeah. So couple of minutes. How are we going to find RT? Tom, take us through what you've got then. RT. Oh, I see. So you split it, have you? Yeah. So you've got. So what we'd have to do there is put that like that, wouldn't we? Then you're going to say, let's call it R23 is R2 plus R3, 1950 plus 1950 equals whatever that is. 3900. Yep. And then
I've done like 1 over.
Okay. 1 over RT.
Over 1 over 390 plus 1 over 1950. Does that make any sense whatsoever? Yes, I'll come on. Yeah.
1950
Yeah.
plus 1 over 3900.
Yes, okay.
Yep. So RT equals, and you've done that maths and pushed the buttons.
Yeah.
Yeah, 1 over RT is equal to 1 over. Yep. Okay. Now, I'm going to put it on another page, right? Because I think maybe a more. Have they all heard of a product over sum method for 2 resistors? Yeah. So an alternative way of doing that is RT is equal to and that's product over sum, so that's 1950 times 3900 over 1950 plus 3900. This bit being the product and this bit being the sum. Yeah, and that's just a little bit more succinct way of writing it. Takes less time, less paper, less time in the exam. Same result, okay? So it don't matter to me which way you do it, as long as that's clear, the method that you used, I don't care, okay? But there's the same amount of marks for doing it that way as there is for doing it in a longhand way. So the choice is up to you, and ultimately you should do it in the way you're more confident with. So going back to here, that means that I, the line current, is E over RT, that's 300 over the 1300, and you should have got, I think, from 231 milliamps. Yep. Second part of the problem, B. New current flowing in each load. So, if we label these I1 and I2, yep, we can calculate them quite easily, can't we? The calculations in this problem are not particularly difficult. It's understanding that system and getting it in a format that you can actually see what the problem is. Yeah? So how do I calculate the current I1? By Ohm's law, that's what? E over, that's got to be R1, 300 over 1950. $154 milliamps. I'll leave you to do I2. Right, where are we? How do we do that one? What do we get? I2. Got to be E over. Yeah. R2 plus R3. We might as well do it all in one go, mightn't we? Yeah. That's 300 over 3900, which comes out at 76.9 milliamps. Yeah. So two different currents now, because effectively that's paired up two of the windings together in series and the other one's in parallel with that. Yeah. Part C. Find the new power dissipated by each load and compare that with problem 1. So if we focus first on R1, how do we calculate the power dissipated by R1? I1 squared R1, so that's 0.154 squared times 1950 equals 46.2 watts. Yep. I got down here that that's the same as it was in problem 1. And if you think back to it, or if you look back at the full system, there, if we look at this one here as being R1, whether we connect that or not, when we deal with just that load, it is that voltage that's across it, so you'd expect the power through that one load to be the same. But because each of these other ones have also got that 300 volts, they're all the same. It's a balanced load. But PR2 is equal to PR3. Both of them must be the same because they've got the current, same current going through them. It's I2 squared times R1 plus R2 to be complete. Yeah? Sorry, R2 plus R3. That is 0.0769 squared times 3,900. Ain't what I get, unless I push the buttons wrong. Oh no, I can see what I've done on this piece of paper. 23 point what? 1. Yeah. It's alright. My answer's wrong. I've put 1950 there instead of 3900. Ah! I'm right and you're wrong. Why? Yeah, and the question says new power dissipated by each load. Those two resistors are still individual loads. So it should be, for each one of those, you've got 1950 ohms, and that is, I got 11.5 rounded to 3 significant figures. Because the question there says new power dissipated by each load, so that's around about, that one is the same as it was. These ones are gone a quarter. We've halved the current. The square relationship means half the current, you quarter the power. Yeah. So each of those two resistors, R2 and R3, are now dissipating a quarter of the power they did when the third phase was connected. So that's a quarter of what it was in problem 1, that one. This is same as problem 1.
So is that generic selling thing you can make three phase that lose at once?
There's half the current in 2 of the loads, and half the total current. It's kept the same current in one load, half the current in the other 2 loads, and if you halve the current, the square relationship here because it's I squared, the relationship with current between power and current, if you halve the current, you'll quarter the power. Yep. That's why that's a good idea to up the voltage on the national grid, because then you bring the current down, and you're every time you halve the current, you quarter the power losses in the cables and all sorts of things. Yep. So
What if you do the favourite motor when they take it down?
yeah, I mean momentum might keep it going, but you know, yeah, yeah. But well, they certainly will vibrate, and they won't last very long. Yeah. Okay. So the third part is the new total power. Sorry, fourth part, D. The total power must it not, PR1, PR2, it's PR3. We'll add them all together. So we got 46.2 plus 11.5 plus 11.5 equals 69.2 watts, and that compares with 193 watts for problem 1. Just less than half. So a third. Compares to the 139 watts for problem 1, sorry. So it's half. Yep. Because half power, if that's a motor, it's half power, but that's a lumpy, it's going to pull around in one bit, but it's not going to do, this ain't going to like it, is it, at all. Right, and then lastly, what was the last part of the problem? That was compare the total power of that from problem 2, which we've already done. Okay, so that's the faulted 3-phase delta system, drop loss of line fault. Yeah. All right. So you might get some problem in the exam on 3-phase systems that towards the end of that problem you start analysing what happens when you lose a phase or something like that. Yeah. Or it might, so I might decide to create an imbalance in a system by loss of phase, because that's what it's done here, it's imbalance, or create imbalance by changing the value of one or more of the resistors so it's imbalanced, like we did last week. Yep. Which one?
The figures below don't match that. In the total